right, in this video, I wanted to cover a particular type of motion that we see in Chapter 4. We're going to actually see this throughout the semester, and so we want to be familiar with it. And what I'm concentrating on today is the idea of circular motion and how do we describe the acceleration when that kind of motion occurs. So you see a picture right here. We have a car and it's moving in a circle. And we're going to start off with the simple case of what we call uniform circular motion. Uniform circular motion means that the speed is constant, but obviously the direction isn't. I'm eventually going to be able to show you that the direction of the acceleration is towards the center of the circular path, but we also want to know what's the magnitude of that acceleration. So we're trying to find something about the acceleration. We want to know the magnitude, and we want to understand why its direction is in the way that I'm showing you on this picture. So these are the things that we want to talk about in this video: the magnitude of this type of acceleration and its direction. So the first thing that we're going to do is we're going to tackle the problem of what is the direction of the acceleration. So here we have a picture of a circle, and you're seeing the direction of the position. So here is just the position at some time t, and so it's here on the circle. And then if we let an amount of time delta t go by, the position is up here. The purple vectors are the velocity vectors. And so there's the velocity vector initially, which we're just calling time t, and then the velocity vector at time t plus delta t. Delta t is the amount of time that we allowed to pass during the two points that we looked at. And I just want to take a closer look and for you to sort of see some of the other details in this picture. So for instance, you notice, so this is the first position vector and this is the second position vector. And notice that they're displaced by an angle of delta theta. So that's going to be the angle that the object has moved through, whatever's going in the circle. You can also see that the displacement vector is between the two heads of the position vectors. That's kind of important because it sets us up to think about sort of geometrically what the change in the vector looks like on the picture. And that's important because right here, what we've done is we've drawn the two velocity vectors, but we'll draw them tail to tail. And so what you can do is you can imagine taking this vector right here and just pulling it down so that it's tail to tail with the original velocity vector. We end up making a similar triangle. So this triangle right here that's made up of the velocity vectors and the change in the velocity is similar to this triangle here. And the reason that it is because they both have an angle between them of delta theta. And so we're going to, I think at some level I'm asking you to believe me on that, but it is true. Now what we see when we put those two velocity vectors together, again, I'm asking you to imagine pulling this vector down here and just putting it right here. Notice that the change in velocity, which is going to give the direction of the acceleration, so keep in mind that the acceleration is equal to the change in the velocity over the change in time. And so now we see the direction of delta v is towards the center of the circle. So that's the first piece of information that we have about this acceleration, is that it's pointed towards the center of the circle. And it should make sense as you think about it, because if we look at this velocity vector from going from here to here, the acceleration vector is resulting in its change, and it does have to kind of move inward in order to stay in the circle. So the next thing we have to figure out is, how big is this acceleration? So we're going to try to figure out its magnitude. And I'm just going to rewrite the idea that the acceleration is the change in the velocity over the change in time. But now we're really just going to think about its magnitude, like how big is this? So I've put the absolute value signs around those things because we're just looking for its magnitude. And we're coming back to our pictures of our similar triangles. This picture looks slightly different, but it still has the same type of information in it. So up here we have the orange dotted line represents a portion of the circular path, and we've allowed the object to move for a small amount of time, delta t. And so we have the first velocity vector and the second velocity vector. And we know that here, right here, if we look at this angle right here, these are the two velocity vectors put together, and then we're looking at the change in the velocity right here. We want to think about these similar triangles, and one of the things that a piece of information that's going to be really helpful to us is if we imagine a circle. Here's my little circle, and I take a piece of that circle where this is, let's just call this angle alpha, and then this is the radius of the circle, and this is the arc length. This is like going from here to here. It's true that this arc length is equal to r times the theta. So we're going to use that piece of information that the arc length is equal to the radius times the theta. And now I want you to translate that to these triangles. Now I know that the third side right here, this is what we're sort of substituting in for the arc length, but we're looking at very small changes. So thinking of the straight piece that completes the triangle as opposed to the curved arc, we're not really introducing any error. So as we look at this triangle, we see that the delta V can be written as V times delta theta. Or, I'm sorry, in this picture they're calling it delta phi. And so that's over delta t. So again, what I've done is I've said, looking at this triangle right here and thinking about this piece, we can say that this has the length equal to the radius, which is the velocity vectors, which have a constant velocity, it is a constant speed, so they're the same length, times the angle that is between them. Now, when I look at this, it's not that helpful yet, but what I'm going to do is I'm now going to use the fact that this triangle here is a similar triangle. And so in this triangle, I can say, I'm going to write it up here, delta S is equal to R delta phi. And I'm going to rearrange this, and delta phi I can write as delta S over R. And so I'm going to substitute in for this angle. I'm going to write it as V delta S over R and then delta t. Now, delta S over delta t can just be written as V so I have two V's on the top and the R on the bottom, and if I simplify this, I get V squared over R. So the magnitude of our acceleration, which I'm going to call, there's a special name for it. So what we're describing so far in this scenario is the acceleration due to an object moving in a circle with a constant speed has this centripetal acceleration, and we're going to say the magnitude of that can be expressed as the velocity squared or the speed squared over the radius of the circle, And we also found that it's towards the center of the circle is the direction. In this picture, we're summarizing at least the idea of the direction. So we have the velocity vector shown for the object moving in the circle, and we have here the radial acceleration. So I want to just emphasize that because we see things written different ways. The radial acceleration is the same as centripetal acceleration. And it's equal to the velocity squared or the speed squared over r. And so I just want you to be flexible because you'll see in different sources it written different ways. In this particular picture, it's labeled as the radial acceleration, and that's because it's along the line that coincides with the radius of the circle. But we most often also call it centripetal acceleration. And so now we can completely describe uniform circular motion and know how we express the acceleration that is experienced during this type of motion. And then the last thing that we want to consider is what if the speed changes? That would be non-uniform circular motion. The non-uniform referring to the fact that the speed isn't uniform. And when that happens, we have another type of acceleration which we call a tangential acceleration. So in this picture right here, you see this blue arrow here represents the centripetal acceleration of this car because of the fact that it's moving in a circle. We would find the magnitude of that using its speed at that instant in time. It still would be v squared over r. Now, this little blue arrow that you see right here represents the tangential acceleration. So we would write the total acceleration would be written as the tangential acceleration plus the centripetal acceleration. And in terms of the magnitude, the tangential acceleration is just how the speed is changing. And so it's hard to see, but I did put absolute value signs between around my velocity there. So it's basically just how's the speed changing with time, and then the centripetal acceleration is equal to v squared over r. Notice in this picture, these two acceleration vectors are perpendicular to each other, and then we see that the resulting acceleration is the one that would, complete the triangle, or it could be the diagonal of the parallelogram they make, which is actually a rectangle. And so we end up with an acceleration that isn't perfectly towards the center of the circle, but at an angle. And how much that angle is will depend on what the relative strengths of these two accelerations are. And so that covers what we need to know about circular motion, both when it's uniform and when it's non-uniform.